Hello students, good morning
Hello, sir.
everyone. So we'll start with the lecture. So today's topic is on the second chapter, which is magnetic field in the material media. And what we will do today is we'll find the magnetic field produced by magnetic material. Now when we say magnetic material, normally the magnetic materials are the metals. I'll just refer the three different types of metals. One is the iron, second is the copper, third is aluminum. So iron, copper and aluminum. Normally these metals or any magnetic materials, they do not produce any magnetic field. If you take a piece of iron or piece of copper or piece of aluminum, it will not attract or repel other magnetic material. That means it is not producing the magnetic field. It is not producing the magnetic field because it has no magnetization. It has no magnetization. It has no magnetization because the resultant magnetic moment of this material is zero. I am saying resultant. Total magnetic moment of all the atoms of that material is zero. So because of that, there is no magnetic moment is zero, resultant magnetic moment is zero. So it is magnetization is zero. Therefore, it will not produce any magnetic field. Now here we are finding the expression for the magnetic field produced by the magnetic material. That means this magnetic material is kept in some external field. When it is kept in external magnetic field, then it will get magnetized. Example, if you take a piece of iron, keep it near the bar magnet, then it behaves like a magnet. It behaves like a magnet, that means it has a magnetization. It has a magnetization, that means there is some resultant magnetic moment. So earlier, outside the field, it has no magnetic moment. Now, in the external field, it gives rise to the magnetic moment. So it has a magnetization. So it produces the magnetic field. Now, the magnetic field which we find here of magnetic material is when it is magnetized. So it is of the magnetized substance. Now to find the magnetic field at any point, what we will do is, we will use this formula which we have used in the first chapter, that magnetic field is equal to the curl of the vector A. A is called as the magnetic vector potential. So we will find the magnetic field using the magnetic vector potential, finding the curl of the magnetic vector potential. And to find out magnetic field, you have to find the magnetic vector potential. That means first you have to calculate a magnetic vector potential. Magnetic vector potential at a given point is mu naught by 4 pi magnetic moment cross product with R2. R2 is the distance of that point Have you done this earlier? Hello?
Yes, sir. So we did this derivation.
You have done it? Okay, this we have done. We have done about
Yes,
the
sir.
densities. We have done about the this thing, densities, magnetic pole density.
So we did.
Hello?
We did magnetic scalar potential and magnetic pole density.
Pole density we have done. Okay, that means this topic is done, no?
Yes, sir.
Okay, then sorry. I'll go to the okay. So that topic already done. Sorry. So we'll take other topic, a source of magnetic field. Okay, source of magnetic field. Now here see what I mentioned. See what I already mentioned in the earlier part this morning, that the magnetic material normally it is not magnetized, but in the external magnetic field it get magnetized. Now that what is called as a magnetization depends on the material. Now suppose if you consider the magnetic material, see if you consider some magnetic material, the magnetization depends upon the material. Then a field produced due to that magnetization again depends upon this material. Say, now if you consider any magnetic material, in the external field, it get magnetized. It get magnetized means it produces the resultant magnetic moment. So because of that magnetization, it will produce the magnetic field. But see, this magnetic field is produced because of the magnetization of the material, and magnetization of the material is because of some external field. See, any material normally it is not magnetized. The resultant magnetic moment is zero. But if you keep it in some external field, then it will get magnetized and it will produce the magnetic field. So now the source of this magnetic field produced by the material is some external field. And that what is that external field that we have to find now. Normally what is done is, sometimes we take a solenoid like this, we take a solenoid and inside we keep the magnetic material. You keep a soft iron, or you can keep aluminum, or you can keep a copper. When you pass a current, because of this current, this material will get magnetized, and then what happened is, this magnetized material will produce the magnetic field. So now the basic source of magnetization is this external field produced by the solenoid or any external field. So that is the source of magnetic field. Now we want to find expression for that, the source of magnetic field. It will be called as the magnetic intensity H. Magnetic intensity H. So see, one is magnetization. Magnetization depends upon the external field. Then magnetic field produced by that material, that depends upon the magnetization. So magnetic field produced by the material depends upon the magnetization, and magnetization produced by the material depends upon external field. So here at some point a magnetic field will be produced. Now this magnetic field is produced because of the magnetization of this material, and this material has been magnetized because it is kept inside a solenoid which is carrying the current I. So now we have to find out some expression which tells about the source of this magnetic field produced by the material. So it is external. Suppose if you increase the current, then magnetization will increase. If the magnetization increases, the magnetic field increases. So that source of magnetic field actually is what is called as the magnetic intensity. Now we have to find out what is that magnetic intensity. So this magnetic intensity has to depend entirely on this external field, external current, or here external field which produces the magnetization. So that is what we are looking out from here. So now this H should not depend upon the magnetization of the material. It should not depend upon this magnetic field produced by it, but it should be independent quantity. So this magnetic intensity is an independent quantity which is responsible to produce the magnetization in the material and thereby producing the magnetic field. So that now expression we have to find out. So that is what will be called as the magnetic magnetic intensity. So now, so far we have seen, in fact, 4 things. One is the magnetic moment. It depends upon the electrons which are orbiting. Then magnetization. It depends upon external field which magnetizes that material, and then the magnetic field. So now this is a fourth quantity. H is a fourth quantity. Now this fourth quantity will describe to us what is that external field which is magnetizing the material. So that we have to find now. Now, to find that, say any magnetized material, say as we have seen in this case, this magnet. See, now what happened is this external field, or example in solenoid, external current will magnetize it. This magnetization will produce a magnetic field. Now this magnetic field in turn produces a more magnetization of the material. So this external magnetic field is produced is due to the atomic current. See, it is produced because of the atomic current. Atomic current means current which are circulating around the nucleus. That charges which are electrons which are circulating around the nucleus. So that atomic currents produce a magnetic moment. Then beside that, transport current, that means regular current, transport current. Now this transport current will be something external. Then, so now what we do here is, we write the magnetic field. See, we will write the magnetic field. So magnetic field produced by any material. See, if you consider the material like this, the magnetic field produced here, first of all, it will depend on this quantity which you had derived earlier. It will depend upon magnetization of the material and the magnetic scalar potential phi. So this expression we have found. Beside that, it will also depend upon that current, external current. So current density. So it's not J suffix m, but simply J. Now this we have seen in the first chapter. The magnetic field produced by the current carrying wire, mu naught by 4 pi, volume integral of vector J. Vector J is nothing but the current density, and R minus R dash. That is the distance of that point. So distance of that point from the element. So that is R minus R dash. R and R dash, they are position vector. R dash is the position vector of the element, and R is a position vector of that point. And R minus R dash is the distance of that point where you are finding the magnetic field from the element. So this is what is written here? The first term is due to the transport current. Normally, example solenoid, because of the current to the solenoid. Then this is produced second and third term. It is due to the circulating current in the magnetic material. So this expression we take. Then we now define what is called as the magnetic intensity. Now this magnetic intensity is the vector quantity, vector H. It is defined taking into account that, see, this is knowing in advance first only, that it is defined this way in such a way that this quantity will entirely depend upon the external field and not the material. So the relation between this external field and this material is 1 by mu naught vector B minus vector M. So afterwards we will show that the H, although it looks like here it depends on B and M, but actually this is only the value it gives. But this H, the physically depends upon the external current. Suppose you keep the material in the solenoid, then it will depend upon the that solenoid only. The physical quantity associated the solenoid. So this we have to simplify and get it. That H will depend only on the solenoid current, in fact, and also number of turns per unit length. So that the material will get magnetized when you keep in the solenoid. So that is the external field. So this is H is defined this way. 1 by mu naught vector B minus M. Now actually we have to show this, that is equal to, in fact we will show that equal to Ni. For a solenoid, we will show it equal to Ni. N is the number of turns per unit length and I is the current. So it is expressed in terms of B and M, but actually its value, you can show that equal to Ni. N is the number of turns per unit length into the current, because normally the material is magnetized by putting inside the solenoid. Now we will simplify to show this. See, here 1 by mu naught is there, then B is this, what you have just now shown, B, by taking the transport current and the material, and minus M. And then what we can do here is, now this mu naught and this mu naught will cancel, this mu naught and this mu naught will cancel, and this M and this M will cancel. So what you get is this term, what you get is this term here, that this mu naught will cancel here, this also cancels here. So what you get here is 1 upon 4 pi, this is 1 upon 4 pi integral j cross r minus r dash divided by r minus r dash cube dv dash minus the gradient of this scalar potential, magnetic scalar potential. Now, if you look at this formula, see what I want to show is this H depends only on the entirely on the external things, not on the material. But here what we know that vector J, see this vector J, we have shown that it is equal to curl of, see we have shown that it is equal to curl of vector M. Curl of vector M. So vector J equal to curl of vector M. That is the curl of the magnetization. So H depends upon the magnetization. See, H depends upon the magnetization. So that means even, see, not only here, but even in this equation, it looks as if H depends on the magnetic material. So this is not a final expression for H. So it appears that since H depends upon J and J in turn depends upon M, it looks that H depends upon the magnetic material. But in the next, later on, we'll show that H will not depend upon magnetization. It will depend only on the external thing that we have to add to see. So this field vector H, in fact, plays an important role in the magnetic theory, particularly in the problem involving the permanent magnet. H is very important for the permanent magnet. Then see, now we are trying to get, see, now we are trying to show that H does not depend upon the material. H depends upon the external thing which is responsible to magnetize that material. So to get that, we go further. So I mentioned that in the next section, I mentioned it here. In next section, it will show that H depends through the differential equation. So that is what we are going to show now. See this, and when we are trying to show that, we use the Ampere's circuital law. This we already proved. Ampere's circuital law in terms of the magnetic field. So this is the differential form. See, curl of vector B equal to mu naught J. This we already proved it in the previous chapter. Now J is that current density and this is the curl of B. Curl of magnetic field produced is mu naught into J. This is the differential form of the Ampere's circuital law. Now we will try to express this in terms of H. B will try to express in terms of H. So now, see, for when you magnetize the material, that magnetic field produced depends upon both the magnetization of the material and also because of the external current. So external current density. So in fact the J is due to the external current and Jm is due to the magnetization current density which we have defined. Then Jm equal to curl of M. See, curl of M, we have written this. Then we got this equation. We try to open this. Mu naught is taken inside. we get this equation. Then we take this on the left hand side. So we get this like this: curl of B minus mu naught, curl of M equal to mu naught J. Then this we divide by mu naught. So here we get 1 by mu naught, and this mu naught cancels. And then we take this del cross, that means curl we take outside. What remains inside is 1 by mu naught, see 1 by mu naught, B and M, and that is equal to J. But we have defined that 1 by mu naught B minus M as H. So we have written is the curl of H equal to J. See, curl of H equal to J. Now this is called as the differential form of the Ampere's circuitry law in terms of intensity. So see, this is the differential form of the Ampere's circuitry law in terms of B, magnetic field. So this is, now this magnetic field depends upon the magnetization. And here the curl of H is something external. And so this is a differential form of Ampere's circuitry law in terms of the intensity H. So this is a differential, another way of writing the Ampere's circuitry law in terms of H. Now we find here that the curl of H equal to J, and J is nothing but a current density. It is because of J is because of transferred current. See, this J is because of transferred current. Now this part is because of the magnetization current. So now we have shown that H entirely depends upon the transport current, which is external to that material. See, this material, you are keeping it inside some solenoid which produces the magnetic field due to the current. So this current density depends upon the current flowing through the solenoid. So here we have shown that this H depends upon the external current, that means external quantity. So in this expression, so magnetization of the material is not involved. So now this H, we call it as a source of magnetic field. So for any magnetic material, the source of magnetic field is H, and H can be written in terms of J. The J is nothing but the transport current density. Then we have found this differential form. We will try to write in terms of the integral form. Just like even this Ampere's circuitry law. Earlier in the previous chapter we have written also in the integral form, and also in fact first we studied integral form and then we got a differential form. First we wrote integral form, that integral of B dot dl equal to this I. So that was integral form. Now this is a differential form. In same way, what we have first found here is a differential form in terms of the H. Now we will find the integral form. To find the integral form, what we do here is, you take the surface integral on both the sides. So you take a surface integral on both the sides. Since the surface integral, you have to write here dot n ds. See, this n cap ds is nothing but the ds vector ds. So dot product, because integrand has to be scalar quantity. So you have to take a dot product here. And in the volume, the surface element is here, vector ds. So it is written as its unit vector into the magnitude, n cap into ds. Same thing on this side. Then on the left hand side, so it is the left hand side, you apply the curl theorem. According to the curl theorem, the surface integral becomes the line integral. See, you consider the surface like this, and this is the curve bounding that is the length. So surface integral becomes the line integral, and curl of the function becomes the function. So that is the curl theorem. So surface integral becomes the line integral, and curl of the function becomes the function. But since it is a line integral, we write here dl, length, and we take a dot product because integrand has to be scalar quantity. And other side we write it as it is. Now this J dot ds, now J is a current density, current by area into area. So that is the current. So this is the current. So this is the current which crosses that area. So example, suppose you have you have a solenoid like this. Then this current will cross the that material many times. So that those number of time. So now this is integral from the Ampere circular law in terms of magnetic intensity. So we have seen two things here. One is Ampere circular law in the integral form. Other is the Ampere circular law in the uh, differential form. So these two things we have seen. Then so now this I will take it next time, that magnetic susceptibility and permeability. Okay. So the next time what we'll do is we'll try to see the different materials. I given the example of the iron, copper, and aluminium. So we'll classify them into the three different types, and we'll define the quantities associated with that. That we'll do next time. Next time, when is the lecture next time? So it will be informed to you, okay, through the common WhatsApp. Thank you very much.
Thank you, sir.
Thank you, sir.
Okay.